Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Here we will learn about different concepts related to civil engineering. Time to enter the world of civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about turbines and pumps. Introduction to hydraulic machine. Hydraulic machines are basically defined as those machines which convert either hydraulic energy into mechanical energy, which will be further converted into electrical energy, or mechanical energy into hydraulic energy. The hydraulic machines which convert hydraulic energy into mechanical energy are known as turbines, and that convert mechanical energy into hydraulic energy is known as pumps. Turbine mainly consist of study of Pelton wheel turbine, Francis turbine, and Kaplan turbine, while pumps consist of centrifugal pump and reciprocating pump. Pumps. Pump is a device which is used to convert mechanical energy into hydraulic energy. Here hydraulic energy refers to potential and kinetic energy of a liquid. Hydraulic pumps are the energy-absorbing machines. Since it requires mechanical power to run. Turbines. Hydraulic turbines are the machines which convert the energy of flowing water into mechanical energy. The mechanical energy developed by a turbine is used in running an electric generator which directly couples to the shaft of the turbine. Thus the mechanical energy is converted into electrical energy. This electrical power is known as hydroelectric power. First we discuss about turbines. As we have already know that turbines are hydraulic machines which convert the energy of flowing water into mechanical energy. The mechanical energy developed by a turbine is used in running an electric generator which directly couples to the shaft of the turbine. Thus the mechanical energy is converted into electrical energy. This electrical power which is obtained from the hydraulic energy of water, is known as hydroelectric power. At present the generation of hydroelectric power is cheapest as compared to power generated by the sources such as coal, fuel, etc. General layout of a hydroelectric power plant. Figure showing general layout of a hydroelectric plant. It consists of the following. 1. A dam constructed across a river or a channel to store water. The reservoir is also known as head race. 2. Pipes of large diameter called penstocks which carry water under pressure from storage reservoir to the turbines. These pipes are usually made of steel or reinforced concrete. 3. Turbines having different types of vanes or buckets or blades mounted on a wheel called runner. 4. Tail race, which is a channel carrying water away from the turbine after the water has worked on the turbines. The water surface in the tail race is also referred to as tail race. Definitions of heads. Gross head, H.G. It is the vertical difference between head race and tail race. Or in simple words, the difference between the head race level and tail race level when no water is flowing is known as gross head. See figure, it is denoted by Hg. Net head, H net head or effective head is the actual head available at the inlet of the to work on the turbine. In net head, when the water is flowing from head race to the turbine, a loss of head due to friction between water and penstock occurs, though there are other losses also, such as loss due to bend, pipe fitting, loss at entrance of penstock and may more. Yet they are very low in magnitude as compared to the loss due to friction. If H.L. is head loss due to friction between penstocks and water, then net head on turbine is given by net head, H equals gross head, H, G. Head loss due to friction, H, L. Where H, G is gross head, H, L is the total head loss during the transit of water from the head race to tail race, which is mainly head loss due to friction. H, F equals 4FLV2/2GD, where F is the coefficient of friction of penstock depending on the type of material of penstock. Lists the total length of penstock. Vis the mean flow velocity of water through the penstock. Dis the diameter of penstock end. G is the acceleration due to gravity. Types of efficiencies. Depending on the considerations of input and output, the efficiencies can be classified as hydraulic efficiency, mechanical efficiency, volumetric efficiency, overall efficiency, hydraulic efficiency. H. It is the ratio of the power developed by the runner of a turbine to the power supplied at the of a turbine. Since the power supplied is hydraulic, and the probable loss is between the striking jet and vane, it is rightly called hydraulic efficiency. It is defined as the ratio of power given by water to the runner of a turbine. Runner is the rotating part of a turbine, and on the runner vanes are fixed to the power supplies by the water at the inlet of the turbine. Runner is basically a rotating component of a turbine, and buckets or vanes will be fixed at the circumference of the runner. Vanes or buckets fixed on the runner are not smooth, and hence there will be hydraulic losses when water will flow through these vanes of the turbine. Therefore, power given by water to the runner of the turbine will be less than the power supplied by the water at the inlet of the turbine. Mathematically, hydraulic efficiency of a turbine is given by H equals power delivered to runner, power supplied at inlet equals RP/WP, where R.P is runner power and W.P is water power. W.P equals rho times G times H/1000, and unit is kilowatt, kW. For water, rho equals 1000 kg cubic meter, WP equals G times H kilowatt, kW. Mechanical efficiency M. It is the ratio of the power available at the shaft to the power developed by the runner of a turbine. This depends on the slips and other mechanical problems that will create a loss of energy between the runner in the annular area between the nozzle and spear. The amount of water reduces as the spear is pushed forward and vice versa, and shaft which is purely mechanical and hence mechanical efficiency. The ratio of the power available at the shaft of the turbine, known as SP or BP, to the power delivered to the runner is defined as mechanical efficiency, M, equals power at the shaft of the turbine power delivered by water to the runner. M equals S.P/RP, where S.P power available at the shaft of the turbine, R.P power delivered to the runner of turbine. Volumetric efficiency. The volume of the water striking the runner of a turbine will be slightly less than the volume of the water supplied to the turbine, as some amount of water will be discharged to the tail race without striking the runner of the turbine. Volumetric efficiency is basically defined as the ratio of the volume of the water actually striking the runner of the turbine to the volume of water supplied to the turbine. Volumetric efficiency will be indicated by V. Volumetric efficiency of a turbine could be written as mentioned here. Volumetric efficiency V equals volume of the water actually striking the runner of the turbine. Volume of water supplied to the turbine. Overall efficiency. Overall efficiency is basically defined as the ratio of the power available at the shaft of the turbine to the power supplied by the water at the inlet of the turbine. Overall efficiency will be indicated by O. Overall efficiency O equals power available at the shaft of the turbine power supplied by the water at the inlet of the turbine. Overall efficiency O equals SP/WP. Overall efficiency is also defined as the product of mechanical efficiency and hydraulic efficiency. Overall efficiency equals mechanical efficiency x hydraulic efficiency. O equals X H. Classification of turbines. According to the action of the water flowing. Impulse turbine, Pelton wheel. Reaction turbine, Francis turbine, Kaplan turbine. According to the main direction of flow of water. Tangential flow turbine, Pelton wheel. Radial flow turbine, Old Francis turbine. Axial flow turbine, Kaplan turbine. Mixed flow turbine, Modern Francis turbine. According to the head and quantity of water required. High head, above 250 m, Pelton wheel. Medium head, 60 m to 50 m, Modern Francis turbine. Low head turbine, less than 60 m, Kaplan turbine. According to the specific speed. Low specific speed, 10 to 35, Pelton wheel. Medium specific speed, 60 to 400, Francis turbine. High specific speed, 300 to 1000, Kaplan turbine. Impulse turbine. In an impulse turbine, fast-moving fluid is fired through an aero nozzle at the turbine blades to make them spin around. In an impulse turbine, the fluid is forced to hit the turbine at high speed. In impulse turbines, a free jet of water strikes the revolving element, runner wheel, of a machine, which is exposed to atmospheric pressure. The total drop in pressure of water takes place in one or more stationary nozzles, and there is no change in pressure of water as it flows through the rotating wheel. Reaction turbine. In reaction turbines, torque developed by reacting to the fluid's pressure. The pressure of the fluid changes as it passes through the turbine rotor blades. The turbine must be fully immersed in the flowing fluid, and the pressure casement is also provided for working fluid. A reaction turbine is one in which the drop in pressure takes place in the rotating wheel. In reaction turbine, the water enters the wheels under pressure and flows over the vanes or blades. In passing over the vanes, the pressure head is converted into velocity head and is finally reduced to atmospheric pressure before leaving the wheel. Also called pressure turbine. Comparison between impulse and reaction turbine. In impulse turbine, the steam flows through the nozzle and strikes on the moving blades. In reaction turbine, steam first flows through the guide mechanism and then flows through the moving blades. In impulses turbine, steam strikes on the moving blades with kinetic energy only. But in the reaction turbine, the steam which glides over the moving blades possesses both pressure and kinetic energy. In impulse turbine, the pressure of steam remains constant during its flow through the moving blades. But in reaction turbine, the pressure of steam reduces during its flow through the moving blades. In impulse turbine, the steam may or may not be admitted to the whole circumference. In reaction turbine, the steam must be admitted to the whole circumference. The blades of the impulse turbine are symmetrical, whereas in reaction turbine it is not symmetrical. The relative velocity of steam in impulse turbine remains constant, but in reaction turbine it increases while gliding over the blades. For the same power developed, the number of stages required in impulse turbine is less, whereas in reaction turbine the number of stages required is more. The steam flow in impulse turbine is radial to the turbine wheel, whereas in reaction turbine steam flow is radial and axial to the turbine wheel. If we talk about the maintenance work, then impulse turbine has less maintenance work as compared with the reaction turbine. Impulse turbine is suitable where discharge is low, and reaction turbine is suitable for medium and high discharge. Pelton wheel is the example of impulse turbine, whereas Francis turbine, Kaplan turbine, etc. are the examples of reaction turbine. There are differences between impulse and reaction turbine as following. In impulse turbine, at inlet, only kinetic energy available. But in reaction, at inlet kinetic energy as well as pressure energy both available. In impulse, water may allow to enter part or whole circumference. But in reaction, water is admitted over the circumference of the wheel. In impulse, blades are only in action when they are in front of the nozzle. But in reaction, blades are in action all the time. In case of impulse, unit is installed above the tail race. But in reaction, unit is kept entirely submerged in water below tail race. In case of impulse, flow regulation is possible without loss. But in reaction, flow regulation is always accompanied by loss. In impulse, relative velocity either remain constant or reduce slightly due to friction. But in reaction, there is continuous drop of pressure during flow, thus relative velocity increased. As the water flows through the runner, the water is under pressure and the pressure energy goes on changing into kinetic energy. The runner is completely enclosed in an air tight casing and the runner and casing is completely full of water. If the water flows along the tangent of the runner, the turbine is known as tangential flow turbine. If the water flows in the radial direction through the runner, the turbine is called radial flow turbine. If the water flows from outwards to inwards, radially, the turbine is known as inward radial flow turbine. On other hand, if water flows radially from inwards to outwards, the turbine is known as outward radial flow turbine. If the water flows through the runner along the direction parallel to the axis of rotation of the runner, the turbine is called axial flow turbine. If the water flows through the runner in the radial direction but leaves in the direction parallel to axis of rotation of the runner, the turbine is called mixed flow turbine. Pelton turbine parts, working and design aspects. What is a Pelton turbine? Pelton turbine is a tangential flow impulse turbine in which the pressure energy of water is converted into kinetic energy to form high-speed water jet, and this jet strikes the wheel tangentially to make it rotate. It is also called as Pelton wheel. The Pelton wheel is among the most efficient types of water turbines. The fluid power is converted into kinetic energy in the nozzles. The total pressure drop occurs in the nozzle. The resulting jet of water is directed tangentially at buckets on the wheel, producing impulsive force on them. Parts and their functions of Pelton turbine. Different parts and their functions of Pelton turbine are as follows. Nozzle and flow regulating arrangement. Runner and buckets. Casing. Braking jet. Nozzle and flow regulating arrangement. The water from source is transferred through penstock to which end a nozzle is provided. Using this nozzle, the high-speed water jet can be formed. To control the water jet from nozzle, a movable needle spear is arranged inside the nozzle. The spear will move backward and forward in axial direction. When it is moved forward, the flow will reduce or stopped, and when it is moved backward, the flow will increase. Nozzle of a Pelton wheel is a circular guide mechanism which guides the water to flow at the desired directions. It also regulates the flow of water. A conical or spear needle operates inside the nozzle in axial direction. The main purpose of the nozzle is to regulate the flow of water through nozzle. When the needle is pushed forward into the nozzle, it reduces area of jet. As air sold, the quantity of water through the jet is also reduced. Similarly, if the spear is pushed back out of nozzle, it increases the area of nozzle and discharge increases. The movement of spear is regulated by hand or by automatic governing arrangement. Runner and buckets. A Pelton turbine consists of a runner, which is a circular disc on the periphery of which a number of buckets are mounted with equal spacing between them. The buckets mounted are either double hemispherical or double ellipsoidal shaped. A dividing wall called splitter is provided for each bucket, which separates the bucket into two equal parts. The buckets are generally made of cast iron or stainless steel or bronze, depending upon the head of inlet of Pelton turbine. The runner is a circular disc carrying number of cup-shaped buckets which are placed at equal spacing around its circumference. Runner is generally mounted on the horizontal shaft with bearings, and the buckets are either casted integrally with the disc or fastened separately. Buckets are made up of cast iron, bronze or stainless steel. Inner surface of the buckets are polished to reduce frictional resistance to the water jet. Casing. The whole arrangement of runner and buckets, inlet, and braking jets are covered by the casing. Casing of Pelton turbine does not perform any hydraulic actions but prevents the splashing of water while working and also helps the water to discharge to the tail race. Steel coverings provided over the runner of Pelton wheel is known as casing. It does not play any hydraulic function, but is necessary to provide the runner against accident. It has the following functions. It prevents accidents. Minimize the wind losses. Stops splashing of water. Facilitates to collect water. Transmission of water to the tail race. Braking jet. Braking jet is used to stop the running wheel when it is not working. This situation arises when the nozzle inlet is closed with the help of spear, then the water jet is stopped on the buckets. But due to inertia, the runner will not stop revolving even after complete closure of inlet nozzle. To stop this, a brake nozzle is provided. The brake nozzle directs the jet of water on the back of buckets to stop the wheel. The jet directed by brake nozzle is called braking jet. Whenever the turbine has to be brought to rest, the nozzle is completely closed. But the runner of Pelton wheel goes on revolving due to inertia. To bring the runner to rest in short time, a small nozzle is provided in such a way that it will direct the jet of water on the back of buckets. It acts as a brake for reducing the speed of the runner. Working of Pelton turbine. The working of Pelton turbine is as follows. The water is transferred from the high head source through a long conduit called penstock. Nozzle arrangement at the end of penstock helps the water to accelerate, and it flows out as a high-speed jet with high velocity and discharge at atmospheric pressure. The jet will hit the splitter of the buckets, which will distribute the jet into two halves of bucket, and the wheel starts revolving. The kinetic energy of the jet is reduced when it hits the bucket, and also due to spherical shape of buckets the directed jet will change its direction and takes U-turn and falls into tail race. In general, the inlet angle of jet is in between 10 to 30. After hitting the buckets, the deflected jet angle is in between 1650 to 1700. The water collected in tail race should not submerge the Pelton wheel in any case. To generate more power, two Pelton wheels can be arranged to a single shaft, or two water jets can be directed at a time to a single Pelton wheel. Design aspects of Pelton turbine. Following are the aspects to be considered while designing the Pelton wheel turbine. Velocity of jet. Velocity of wheel. Angle of deflection of jet. Mean diameter of the wheel. Jet ratio. Bucket dimensions. Number of jets. Number of buckets. Velocity of jet. The velocity of the jet at inlet is given by velocity of jet equation V. 1 equals C V, where C V equals coefficient of velocity equals 0.98 or 0.99. H equals net head on turbine. Velocity of wheel. The velocity of wheel, U, is given by velocity of wheel equation U equals where equals speed ratio equals 0.43 to 0.48. Angle of deflection of jet. The angle of deflection of jet after striking the buckets is taken as 1650 if no deflection angle is given. Mean diameter of the wheel. The mean diameter or the pitch diameter D of the Pelton turbine is given by U equals /60 or D equals 60 U. Jet ratio. It is defined as the ratio of the pitch diameter, D, of the Pelton turbine to the diameter of the jet, D. It is denoted by M and D is given as M equals D/D. Jet ratio, M, lies between 11 to 16 for maximum hydraulic efficiency. However, in most of the cases it is taken as 12. Bucket dimensions. Bucket's dimensions are designed in such a way that its breadth should be 3 to 4 times of diameter of jet, length should be 2 to 3 times of diameter of jet, and thickness should be 0.8 to 1.2 times the diameter of jet. Number of jets. It is obtained by dividing the total rate of flow through the turbine by the rate of flow of water through a single jet. In general, number of jets are limited to 2 in case of vertical runner and 6 in case of horizontal runner. Number of buckets. The number of buckets, Z, on a runner is given by Z equals 15 plus D/2D equals 15 plus 0.5 m equation for number of buckets where d equals pitch diameter, d equals diameter of jet, m equals jet ratio. Applications. Pelton wheels are the preferred turbine for hydropower, when the available water source has relatively high hydraulic head at low flow rates, where the Pelton wheel is most efficient. Thus, more power can be extracted from a water source with high pressure and low flow than from a source with low pressure and high flow, even when the two flows theoretically contain the same power. Also, a comparable amount of pipe material is required for each of the two sources, one requiring a long thin pipe, and the other a short wide pipe. Pelton wheels are made in all sizes. There exist multi-ton Pelton wheels mounted on vertical oil pad bearings in hydroelectric plants. The largest units can be up to 200 megawatts. Features of Pelton turbines. Pelton turbines are used where the water source has a relatively high hydraulic head at low water flow rates. Pelton wheels can be designed for all sizes based on the objective. Kaplan Turbine-its components, working and application. Kaplan turbine works on the principle of axial flow reaction. In axial flow turbines, the water flows through the runner along the direction parallel to the axis of rotation of the runner. The water at the inlet of the turbine possesses both kinetic energy as well as pressure energy for effective rotation the blades in a hydropower station. In 1913, an Austrian professor Victor Kaplan, who developed this turbine, combined automatically adjusted propeller blades with automatically adjusted wicket gates to achieve efficiency over a wide range of flow and water level. It is also called as propeller turbine and evolved from the Francis turbine. It is capable of working at low head and high flow rates very efficiently, which is impossible with Francis turbine. The main advantage of Kaplan turbines is its ability to work in low head sites, which was not possible with Francis turbines. Kaplan turbines are widely used in high flow, low head power production. The Kaplan turbine is an inward flow reaction turbine, which means that the working fluid changes pressure as it moves through the turbine and gives up its energy. The design combines radial and axial features. The inlet is a scroll-shaped tube that wraps around the turbine's wicket gate. Water is directed tangentially through the wicket gate and spirals onto a propeller-shaped runner, causing it to spin. The outlet is a speculally shaped draft tube that helps decelerate the water and recover kinetic energy. The turbine does not need to be at the lowest point of water flow, as long as the draft tube remains full of water. A higher turbine location, however, increases the suction that is imparted on the turbine blades by the draft tube that may lead to cavitations due to the pressure drop. Typically, the efficiencies achieved for Kaplan turbine are over 90%, mainly due to the variable geometry of wicket gate and turbine blades. This efficiency, however, may be lower for very low head applications. Since the propeller blades are rotated by high-pressure hydraulic oil, a critical design element of Kaplan turbine is to maintain a positive seal to prevent leakage of oil into the waterway. Kaplan turbines are widely used throughout the world for electrical power production. They are especially suited for the low-head hydro and high-flow conditions, mostly in canal-based hydropower sites. Main components of Kaplan turbine. The main parts of Kaplan turbine are: scroll casing. It is a spiral type of casing that has decreasing cross-section area. The water from the penstocks enters the scroll casing and then moves to the guide vanes, where the water turns through 90 degrees and flows axially through the runner. It protects the runner blades, guide vanes and other internal parts of the turbine from an external damage. Guide vane mechanism. It is the only controlling part of the whole turbine, which opens and closes depending upon the demand of power requirement. In case of more power output requirements, it opens wider to allow more water to hit the blades of the rotor, and when low power output requires, it closes itself to cease the flow of water. If guide vanes is absent, then the turbine cannot work efficiently and its efficiency decreases. Draft tube. The pressure at the exit of the runner of reaction turbine is generally less than atmospheric pressure. The water at exit cannot be directly discharged to the tail race. A tube or pipe of gradually increasing area is used for discharging water from the exit of turbine to the tail race. This tube of increasing area is called draft tube. One end of the tube is connected to the outlet of runner, while the other end is submerged below the level of water in the tail race. Runner blades. The heart of the component in Kaplan turbine are its runner blades, as it the rotating part which helps in production of electricity. Its shaft is connected to the shaft of the generator. The runner of this turbine has a large boss on which its blades are attached, and the blades of the runner is adjustable to an optimum angle of attack for maximum power output. The blades of the Kaplan turbine has twist along its length. Working procedure of Kaplan turbine. The water coming from the penstock is made to enter the scroll casing. The scroll casing is made in the required shape that the flow pressure is not lost. The guide vanes direct the water to the runner blades. The vanes are adjustable and can adjust itself according to the requirement of flow rate. The water takes a 90-degree turn, so the direction of the water is axial to that of runner blades. The runner blades start to rotate as the water strikes due to reaction force of the water. The runner blades has twist along its length in order to have always optimum angle of attack for all cross-section of blades to achieve greater efficiency. From the runner blades, the water enters into the draft tube, where its pressure energy and kinetic energy decreases. Kinetic energy gets converted into pressure energy, results in increased pressure of the water. The rotation of the turbine is used to rotate the shaft of generator for electricity production. Application of Kaplan turbine. Kaplan turbines are widely used throughout the world for electrical power production. It can work more efficiently at low water head and high flow rates as compared with other types of turbines. It is smaller in size and easy to construct. The efficiency of Kaplan turbine is very high as compares with other hydraulic turbine. Disadvantage of Kaplan turbine. The only disadvantage of Kaplan turbine is cavitation, which occurs due to pressure. Drop in draft tube. Use of draft tube and proper material, generally stainless steel. 4. The runner blades may reduce the cavitation problem to a greater extent. Features of Kaplan turbines. The important applications of Kaplan turbines are: electrical power production throughout the world. Suitable for lowest head hydro sites and high flow conditions. Kaplan turbines can work with as little as 0.3 m head at a highly reduced performance given that sufficient flow exists. The design, manufacture, and installation is expensive but can operate for decades. Kaplan turbines designed individually for a site can give the highest possible efficiency of around 90%. Francis Turbine-its components, working and application. Francis turbine is a combination of both impulse and reaction turbine, where the blades rotate using both reaction and impulse force of water flowing through them, producing electricity more efficiently. Francis turbine is used for the production of electricity in hydropower stations. Majorly there are two turbines flow patterns on which they work, namely radial and axial flow concepts. An American civil engineer by name, James B. Francis in Lowell, Massachusetts, comes up with an idea of combining both impulse and reaction turbine where water enters the turbine radically and exits axially. The Francis turbine is a reaction turbine where water changes pressure as it moves through the turbine, transferring its energy. A watertight casement is needed to contain the water flow. Generally, such turbines are suitable for sites such as dams where they are located between the high-pressure water source and the low-pressure water exit. Francis turbines are the most common water turbine in use today. They operate in a water head from 40 to 600 meter, 130 to 2,000 feet, and are primarily used for electrical power production. The main reason of higher efficiency of Francis turbine lies in the design of blades. These blades rotate using both reaction and impulse force of water flowing through them. Due to the use of this type of turbines, the main problem faced due to the water head availability is eliminated as the turbine uses both the kinetic and potential energy to produce power. For this, it is also known as mixed flow turbine. Main components of Francis turbine. The major components of Francis turbine are: spiral casing. Spiral casing is the inlet medium of water to the turbine. The water flowing from the reservoir or dam is made to pass through this pipe with high pressure. The blades of the turbines are circularly placed, which mean the water striking the turbine's blades should flow in the circular axis for efficient striking. So the spiral casing is used, but due to circular movement of the water, it loses its pressure. To maintain the same pressure, the diameter of the casing is gradually reduced, so as to maintain the pressure uniform, thus uniform momentum or velocity striking the runner blades. Stay vanes. Stay vanes and guide vanes guides the water to the runner blades. Stay vanes remain stationary at their position and reduces the swirling of water due to radial flow, as it enters the runner blades, thus making turbine more efficient. Stay ring consists of an upper and lower ring connected by welded stay vanes. The stay vane's purpose is to absorb the axial forces on the inside of the spiral casing. The vanes are given a favorable hydraulic shape to affect the water flow minimally. Guide vanes. Guide vanes are not stationary, they change their angle as per the requirement to control the angle of striking of water to turbine blades to increase the efficiency. They also regulate the flow rate of water into the runner blades, thus controlling the power output of a turbine according to the load on the turbine. Runner blades. The performance and efficiency of the turbine is dependent on the design of the runner blades. In a Francis turbine, runner blades are divided into two parts. The lower half is made in the shape of small buckets so that it uses the impulse action of water to rotate the turbine. The upper part of the blades use the reaction force of water flowing through it. These two forces together makes the runner to rotate. The runner consists of a hub, a shroud, and runner blades connecting them. The runner converts the energy in the water to rotating motion and torque. The torque is transferred to the turbine shaft through a bolt friction joint or a combined friction shear joint. The runner can either be casted or welded. For a welded design, the hub and shroud is usually cast and welded together with hot pressed plate vanes. The number of blades depends upon the operating head. Runners with higher head will require a higher number of blades, this is mainly because of strength consideration. Increasing the number of blades reduce the pressure loading on the blade, which will help to avoid cavitation and also prevent separation at the runner inlet during low loads. An increase in the number of blades also leads to more contact surface through the runner and thereby an increase in the friction losses. The thickness of the runner blades has to be large enough to withstand the hydraulic forces the blade is exposed to. For high-head Francis turbines, it is preferred to shape the blade in such a way that the main part of the hydraulic energy is utilized at the beginning of the blade. In this area, the pressure difference from the pressure to the suction side will be large and thereby also the forces on the blade. It is therefore usual to have an increased thickness of the blade near the inlet and let the blade get thinner towards the outlet. Draft tube. The pressure at the exit of the runner of reaction turbine is generally less than atmospheric pressure. The water at exit cannot be directly discharged to the tail race. A tube or pipe of gradually increasing area is used for discharging water from the exit of turbine to the tail race. This tube of increasing area is called draft tube. One end of the tube is connected to the outlet of runner while the other end is submerged below the level of water in the tail race. How does a Francis turbine work? The water is allowed to enter the spiral casing of the turbine, which lead the water through the stay vanes and guide vanes. The spiral case is kept in decreasing diameter so as to maintain the flow pressure. The stay vanes, being stationary at their place, removes the swirls from the water, which are generated due to flow through spiral casing, and tries it to make the flow of water more linear to be deflected by adjustable guide vanes. The angle of guide vanes decides the angle of attack of water at the runner blades, thus make sure the output of the turbine. The runner blades are stationary and cannot pitch or change their angles, so it's all about the guide vanes which controls the power output of a turbine. The performance and efficiency of the turbine is dependent on the design of the runner blades. In a Francis turbine, runner blades are divided into two parts. The lower half is made in the shape of small buckets so that it uses the impulse action of water to rotate the turbine. The upper part of the blades use the reaction force of water flowing through it. Thus runner blades make use of both pressure energy and kinetic energy of water and rotates the runner in most efficient way. The water coming out of runner blades would lack both the kinetic energy and pressure energy, so we use the draft tube to recover the pressure as it advances towards tail race. But still we cannot recover the pressure to that extent that we can stop air to enter into the runner housing, thus causing cavitation. In another way working is explained, water flows from the penstock into the spiral casing. In the spiral casing the water is distributed around the complete periphery. The water is then guided by the stay vanes and guide vanes in the correct angle towards the runner. The guide vanes are adjustable and can change the angle depending on the inlet and outlet conditions of the turbine. They are controlled by a governor servo motor. The runner transfers the energy from the pressure and velocity in the water to a rotational momentum. The water exits through a draft tube that extracts the remaining energy in the water. The torque produced in the runner is transferred to a power-producing generator through a shaft. Features of Francis turbines. The Francis turbines operate best when its casing is completely filled with water at all times. It can be designed for a wide range of heads and flows. These turbines are not only used for electrical production, but also for the pump storage. Applications of Francis turbine. Francis turbine is the most widely used turbine in hydropower plants to generate electricity. Mixed flow turbine is also used in irrigation water pumping sets to pump water from ground for irrigation. It is efficient over a wide range of water head and flow rate. It is most efficient hydro turbine we have till date. Francis turbines may be designed for a wide range of heads and flows. This, along with their high efficiency, has made them the most widely used turbine in the world. Francis-type units cover a head range from 40 to 600 m, 130 to 2000 feet, and their connected generator output power varies from just a few kilowatts up to 800 MW. Large Francis turbines are individually designed for each site to operate with the given water supply and water head at the highest possible efficiency, typically over 90%. In addition to electrical production, they may also be used for pump storage, where a reservoir is filled by the turbine, acting as a pump, driven by the generator acting as a large electrical motor during periods of low power demand, and then reversed and used to generate power during peak demand. Advantages and disadvantages of a Francis turbine over a Pelton wheel. Advantages: variation in the operating load can be more easily controlled. The ratio of maximum and minimum operating heads can be even too. The operating head can be utilized even when the variation in the tail water level is relatively large when compared to the total head. The mechanical efficiency of Pelton wheel decreases faster with wear than Francis turbine. The size of the runner, generator, and powerhouse required is small and economical if the Francis turbine is used instead of Pelton wheel for same power generation. Disadvantages: water which is not clean can cause very rapid wear in high-head Francis turbine. The overhaul and inspection is much more difficult comparatively. Cavitation is an ever-present danger. The water hammer effect is more troublesome with Francis turbine. If Francis turbine is run below 50% head for a long period, it will not only lose its efficiency but also the cavitation danger will become more serious. Factors affecting the selection of hydraulic turbines. Following are the factors affecting selection of hydraulic turbines: head, specific speed, rotational speed, efficiency of the turbine, cavitation, disposition of turbine shaft, part load operation. Head. The hydraulic turbine selected should be decided based on the head, and for different head ranges different turbines are suitable. Heads are divided into 5 types and suitable turbines for them are given in the table below. Head. Head range in meters. Suitable turbine. Notes: very low head 310. Bulb turbine. Kaplan turbines are also suitable but uneconomical for very low heads. Low head 1060. Kaplan turbine. Propeller turbines are also suitable up to 15 m head, but there should not be load variations. Medium head 6150. Francis turbine. High head 15350. Pelton or Francis turbine. One of them is decided based on the specific speed. Very high head. Greater than 350. Pelton turbine. Specific speed. The specific speed is high for turbines which works under high heads and low flow rate. Similarly, specific speed is low for a turbine which works under the low head and high flow rate. When the specific speed of the selected turbine is not up to the required range, then the rotational speed of turbine reduces, thus the capacity of plant reduces. However, medium specific speed turbines such as Francis turbines can generate high rotational speed. Type of turbine. Specific speed range. Pelton turbine 1070. Francis turbine 8400. Kaplan turbine 301,000. Bulb turbine 1200. Rotational speed. The rotational speed of the turbine depends upon the specific speed of the turbine, frequency, and number of pair of poles in the electric generator. So, the specific speed of the selected turbine should produce the same amount of rotation speed of the generator. Efficiency of turbine. The efficiency of the turbine selected should be as high as possible, and it is considered for various working conditions of turbines. Different turbines in decreasing order of their overall efficiency are as follows. Efficiency of turbines equals Francis turbine, Kaplan turbine, Pelton turbine. Cavitation. Cavitation mainly occurs in the case of reaction-type turbines. So, while selecting the turbine, cavitation factor should be determined for that particular turbine to check whether it is in a safe zone or not. Cavitation factor depends upon the specific speed of the turbine. It is important, especially in the case of Kaplan, propeller, and bulb-type turbines. Disposition of turbine shaft. Based on the previous experiences, it is recommended that the horizontal shaft arrangement is best suitable for large-size impulse turbines such as Pelton turbine, etc. Similarly, in case of large-size reaction turbines such as the Kaplan turbine, Dirichlet turbine, etc., vertical shaft arrangement is recommended. Part load operation. In general, the efficiency of the turbine is maximum when it is running with a designed load condition. When the part load or overload condition arises, the efficiency reduces, which is uneconomical. In that case, Dirichlet turbine or Kaplan turbine is recommended. The basic difference between Pelton, Francis, and Kaplan turbines. SL no criteria. Pelton turbine, Francis turbine. Kaplan turbine 1 TYP. Pelton turbine is an impulse-type water turbine. Francis turbine is an inward flow reaction turbine. Kaplan turbine is a propeller-type reaction turbine. 2 HYDROELECTRIC. It is used for high heads ranging from 250 to 1000 m. The operating water head of a Francis turbine ranges from 40 to 600 m. It is used for low heads ranging from 10 to 70 meters. 3 runner. The diameter of the runner varies from 0.8 to 0.6 m. The diameter of the runner varies between 0.91 to 10.6. The diameter of the runner varies between 2 to 11 meters. No. Criteria: Pelton turbine, Francis turbine, Kaplan turbine. 4. Direction of flow of water through the blades. The flow of water is tangential to the runner. Hence it is also called as tangential flow impulse turbines. The flow of water through the blades combines both radial and axial flow. The flow of water is axial through the blades. 5. Power generation. Power generated is about 400 MW. The power generated by a Francis turbine is about 800 MW. The output power obtained varies from 5 to 200 MW. 6. Speed. The rate of speed in a Pelton turbine changes from 65 to 800 rpm. The speed of the turbine ranges from 75 to 1000 rpm. The rotational speed varies from 69.2 to 429 rpm. No. Criteria: Pelton turbine, Francis turbine, Kaplan turbine. 7. Discharge required. The required discharge for the working of a Pelton turbine is low. Medium discharge is required for the working of the Francis turbine. A Kaplan turbine requires high discharge for efficient working. 8. Type of energy. The Pelton turbines uses kinetic energy and converts into mechanical energy. The Francis turbine converts potential energy into mechanical energy. The Kaplan turbine uses both kinetic and potential energy, which then is converted into mechanical energy. 9. Efficiency. The efficiency of a Pelton turbine is about 85%. The efficiency of a Francis turbine is about 90%. The Kaplan turbine gives higher efficiency, about 90%. Thank you for watching. Pumps will be discussed in another video.
Thank you for watching. Please subscribe to the channel and press the bell icon.